Welcome all of you. So quickly we'll start with the MCQs of physics. Okay, few things I just want to bring to your notice in case it is asked as an MCQ. So let's start. Here the very first thing I want to mention here is movement of a couple. Okay, movement of a couple. These are very small things which can be made into an MCQ. Okay, now movement of a couple, if this is the distance between the two couples and these are the two forces, equal and opposite forces, okay, then moment of a couple is this F into this full distance D. Now even if I put even after I put up my videos in moments, I can see people have this doubt here. A lot of doubt is here. People don't understand the difference between moment of a couple and moment of an uniform rod, where it is taken for two forces, it is taken about the pivot. Okay, so moment of a couple is different thing because it is two equal and opposite forces. Here it need not be equal forces. Okay, if they are not in equilibrium, if it is not in equilibrium, it need not be equal. So couple is a totally different thing where this full distance is asked along with this. So moment becomes F into D. Be very careful. Okay, so where you both are not the same things. Okay, so they can trick you with this. So this was just a reminder that moment of a couple takes the full distance, perpendicular distance between the two forces. Okay, now talking about equilibrium of forces, the net force on a raindrop. Okay, a raindrop will not have any weight when it falls on us. The reason is the first force, that is the buoyant force, okay, and the second force that is working is the force of friction. You can also call it the force of, you can also say this is the force of viscosity of the air. Okay, and what are these two forces balancing? These two forces are basically holding up the weight of the water drop. Okay, so that is why, since this, so therefore a raindrop only falls down at a, it only falls down at a constant speed. It will not have an accelerated motion. Okay, because the mg is being balanced by these two things. Okay, so this is one example of a dynamic equilibrium. Okay, when a raindrop falls or a plane moving at a constant velocity. Okay, so here also you can see this is a dynamic equilibrium because the plane is still moving in spite of forces which are acting like this. That's the weight of the plane, and then this is the upward lift. Okay, or you can say the buoyant force on the plane. Okay, so now these are examples of dynamic equilibrium. Just a reminder, CG. Okay, CG questions can come in MCQs. So CG is of a solid cone is 1/4. For a solid cone, CG is from here of this whole height, it is h by 4, at h by 4. Okay, so this is 1/4, from 1/4 to the of the base. So 1/4 of the height from the base, that is CG. Coming to centrifugal force. Centrifugal force. Now this is very important. All of you always say it is a false force. Okay, it is not a force, it's a false force. Not only is it a false force, it is a, they call it a fictitious force which does not exist. Okay, but then we assume it is there for certain reasons. Now I'm in MCQs, I'm not going into the details of this, but then very often, you know, we think that centrifugal force and centripetal force, they can ask you a question like this: centrifugal and centripetal. Okay, these two forces are like Newton's third law. One of them is an action, the other one is a reaction. No. Okay, so they can trick you over here in MCQs. Centrifugal and centripetal forces are not action and reaction clearly, because they are clearly working on the same object. Action and reaction always happens on different objects. So we can't apply Newton's third law over here. Now work is equal to F into S. You know it. F into displacement. Okay, work is F into displacement. Work is a scalar quantity. Okay, work is a scalar quantity. So if work is a scalar quantity, this is vector, this is also vector, but work is scalar. Okay, so remember why it is, in spite of these being vectors, this is a scale you learn in 11th standard. Now here again we have two ways of defining work. If the force and the displacement is happening in the same line, no problem. Okay, if force and displacement happens in the same line, we don't have any problem only. But then it is not necessary that force and displacement will happen in the same line. Force is coming along this, displacement is happening at an angle of theta. Then we'll have to take the horizontal component s cos theta of displacement, and then our work becomes F is equal to Fs cos theta. Okay, now here you can take it along this line also. Okay, the ultimate thing is work and displacement has to go in the same line. So here we took force and we took s cos theta, that is we took the component of displacement and we got our work. Similarly here we will take the component of force and we will take the into s. Okay, that is Fs cos theta, whichever way. So we took the component of force here. Okay, this angle is also theta, and so now again see s and f cos theta is in the same line. Here f and s cos theta is in the same line. Here f cos theta and s is in the same line. Okay, so either you take this line or you take this line, but align both of them. That is, the displacement and the force has to be in the same line. So these are two ways of writing force, and this is one of ICSE's favorite. So see to it that you are understanding. Let's talk about negative force now. Negative work, sorry. Okay, now what is negative work? Few examples of negative work. When we get that in negative work, when we have examples of negative work, they might even ask for it. Okay, now this happens when force opposes the motion. One is for friction. Okay, one is for friction and the other one is, you can say, you are throwing something upwards. Okay, you are throwing a ball upwards. So actually force of the weight of the ball is working downwards. That's the force due to gravitational acceleration due to gravity, but you are throwing it against the force of gravity, and hence, so throwing up a ball can also be counted as a negative work. Okay, so remember force is working here now and work is being done like this. Then the angle between the force and the work, okay, angle between F and S is a 180 degree, and cos 180 degree is a -1. So even that way it becomes work is equal to minus F into S. Okay, this is the reason cos 180 is a -1. So these are two examples of negative work. I just want to remind you, work when something is moving in a circular path is 0. Work is equal to 0 because the displacement in a circular path, initial and final point is same. Therefore, S is equal to 0. Therefore, whatever the F is, finally work is 0 because F into S is work. So ICSE loves asking graphs. Okay, here if I have something like this, here I have displacement. I have another one here force, here displacement. Okay, now this portion, you have done some things like this in 9th standard. This is the work done. Okay, this is the work done by this force when it is doing this much displacement graphically. Okay, here this area is the work done. Okay, this area is the work done, force into displacement. This is a constant force. F is constant. Remember, this is not a constant force, means if force is varying, F is equal to ma, then if they ask you in which of these there is a variable acceleration, of course acceleration will be there in that also, that is increase in speed will be there. As long as force is there, increase in speed will be there, but that is going to happen at a constant rate. Here F is equal to ma is there, but a is not happening constantly. There won't be a steady change in accelerate in velocity. Okay, the velocity will sometimes increase and sometimes increase less, sometimes increase more. Okay, I can't say that it is retarding anywhere because it is showing a constant increase in force. So I can't say that it is sometimes accelerating, sometimes retarding. No, it is accelerating, sometimes small acceleration, sometimes bigger acceleration. Acceleration is varying in this case. Okay, the work done by a force is equal to the potential energy, isn't it? The potential energy, because if you are lifting up a heavy load, you are lifting up a heavy load to this height h, here it is mgh. These are very simple things. So the force against which you have worked to lift it up is this, right? Because the weight of the body is mg. You have brought this up here, this one you have brought here. The displacement is a h. So the work done in moving something, okay, is equal to, moving something to a height is always equal to the potential energy of the body. Not just that, it's not always a question of height. If you have a spring like this and you're pressing it down, this becomes the displacement, okay, and you're applying a force to it. So again, the potential, that same energy gets stored in it because of law of conservation of energy. So here it gets stored into it, and that makes it the potential energy of the body. Okay, one formula just in case you don't forget. Okay, power is force into velocity. They ask small numericals in my work part chapter. I have done numericals based on this because I feel this is one formula somehow you all don't remember. So small question can be asked. Okay, this is in Newton, this is meters per second, and this is going to be in watts. Okay, let's move on to the next question. Another unit of G, generally we know G as meters per second square, right? Another unit of G, what can it be? Okay, so that can be Newton per kg. Now they can give 4 units. It's very common to ask questions about units in MCQ. Don't miss this. Newton per kg is a correct unit of gravity, acceleration due to gravity. I'll just convert it to meters per second square and show you. Okay, Newton is force. Okay, that is MA, right? MA. Now MA means M is in kg. Yes. So the unit here is kg mass and acceleration is meters per second square. Kg to the power minus 1. So we get back our meters per second square. So these two are the one and they are the same units. So if they ask this in one of the options in MCQ, please put a tick here. Okay. There's something called work energy theorem. Okay, this theorem actually makes your sum simpler. I have done a sum based on this in my work power energy video. Here, work energy theorem, it simply says if a body is here and it has been moved here it had a velocity of u, here it got a velocity of v, how much of work has been done by it. Kinetic energy at this position is, mass of the body is m, and kinetic energy here is this. Okay, so this is work is half m v square minus half m u square. Okay, kinetic energy is half m v square minus half m u square. That is the difference in kinetic energies between these two positions. So here half mv square minus half mu square, that is the work done by this body. It can apply to a vehicle also. Okay, it can apply to anything. Now if a body is being thrown up with a velocity u, okay, and it goes to a height h, naturally mgh is its potential energy, and here the kinetic energy with which it was thrown up was half mu square. Okay, the same kinetic energy due to law of conservation of energy gets converted here to potential. You know that over here in all these points, if this potential is a 500, everywhere it's a 500, 500, 500. So half mu square is equal to mgh. Okay, and then u square is 2gh. U is equal to root over 2gh. U is root over 2gh. Okay, so u is root over 2gh. So the velocity with which it is thrown up can also be written as this kind of an expression. Please note from where we are getting it. Okay, so if they say how to connect the velocity along with the height, we have connected it here. Let's come to pulleys. Okay, I'm trying to take as many MCQs as possible. I shall be taking more in the next video. Okay, so keep watching very soon. So here pulleys. In pulleys, the block and tackle one. Okay, so here if you have 3 of them and then you have 2 of them. Now the rule is this one should have either one more than this set, or it can have equal. So it can be 7 and 6, it can be 5 and 4, okay, but then this cannot be 5 and that cannot be 4, okay. So either equal, both equal, or this has to be one more, okay. Now the thing is how to do the threading. There, be careful how to do the stringing. They usually tell you, they give you this kind of a set and they say show the path of the string. So what do you do for that? Now, if both have equal number of pulleys, okay, equal number of these, then in case of equal number in both, then the string will start from the upper one. Okay, this is something to be remembered. Okay, because there you can't be confusing. String starts from the upper one and starts like this, because there will be a hook here, there will be another hook here. Okay, and then it goes like this. Okay, now if they are unequal, that is, unequal means only upper one can be bigger, in that case the string will start from the lower one and start. Okay, in that case string starts from the lower one. Thing to be remembered. Now, every time you can't be wasting time in calculations or diagram. Okay, if in block and tackle, if load moves by d distance, effort will move by nd. Remember this. So if there are 5 of them, okay, load moves by 5, okay, let's say 1 meter, effort will move by 5 meters. Okay, so that was it in this video. I shall come up with more videos till Sunday. I shall be uploading more videos, so please remember these things, and more will be coming up in from electricity, electromagnetic induction, and then of course light. Okay, in the next video. Bye then.